This section examines rim sizes and designations. To ensure correct fit between a tire and rim, all manufacturers of wheels and tires comply with standard dimensions as recommended by tire and rim associations. The width of the rim is the distance across the rim flanges at the bead seat. Its diameter is the distance across the center of the rim from bead seat to bead seat. The shape of well-based rims is provided by a letter code, such as J, K, JJ, KK. The width of the rim and the diameter is traditionally stated in inches. A rim designated 7 JJ by 14 would refer to a rim measuring 7 inches across the rim flanges and 14 inches in diameter from bead seat to bead seat, with the profile conforming to a JJ code. The rim width and diameter can also be stated in millimeters. Metric rims are not interchangeable with imperial rims. The tire must be an exact fit on the rim to fulfill a number of functions. It ensures that the narrow contact area between the beads of the tire and the rim will seal the air in a tubeless tire. It transfers all the forces between the tire and the wheel without slipping or chafing. It ensures the friction between the tire and the rim prevents the tire turning on the rim. This section examines types of wheels. Wheels must be strong enough to carry the mass of the vehicle and withstand the forces that are generated during use. Some are made from steel. They are pressed in two sections: the wheel center, with a flange or disc that is drilled for the wheel fasteners, and the rim. They are then welded together. Others are made from cast aluminium alloy. Alloy wheels are lighter than similar steel wheels. And since aluminium is a better heat conductor than steel, alloy wheels dissipate heat from brakes and tires more quickly than steel wheels. The wheel center must accurately locate the wheel rim centrally on the axle. It must also provide the required distance from the center line of the wheel to the face of the mounting flange. This is called offset. On this wheel, the offset is marked. It is 45 millimeters. Offset is important because it brings the tire center line into close alignment with the larger inner hub bearing and reduces load on the stub axle. This allows the inside of the wheel center to be shaped to provide space for the brake assembly, usually located inside the wheel. Ventilation slots allow air to circulate around the brakes. In some cases, wheels are directional to assist the airflow. The rim must be accurately shaped and dimensioned, and strong enough to support the tire under the load of the vehicle and the forces generated by the motion of the vehicle. Passenger cars normally use rims which are of well-based or drop-center design. The drop center is used for mounting and demounting the tire onto the rim. When inflated, the tire is locked to the rim by tapering the bead seat towards the flange or by safety ridges or humps close to the flange. In the event of sudden deflation or blowout, safety ridges prevent the tire moving down into the well. This helps maintain control of the vehicle while it is being braked. Well-based rims can also be used on heavy commercial vehicles for tubeless tires. The rims are referred to as 15-degree drop center rims because the bead seats are inclined at 15 degrees towards the flange. The taper gives a good grip and an airtight seal between the tire beads and the rim. The low flanges and drop center allow the special size, flexible tubeless truck tires to be mounted and demounted in a similar manner to that used on smaller passenger car tires. The stiff sidewalls of larger cross-ply tires mean they cannot be mounted and demounted in this way, and many four-wheel drive and commercial vehicles use a flat base demountable flange rim. When all of the air is removed from the tire, One flange can be removed so the tyre can be demounted. Wheels are fastened to the hubs by wheel studs and nuts. They're highly stressed by loads from the weight of the vehicles and the forces generated by its motion, and they're made from heat-treated, high-grade alloy steel. The threads between the studs and nuts are close-fitting and accurately sized. All wheel nuts must be tightened to the correct torque, otherwise the wheel could break free from the hub. This section examines tyre construction. A tyre provides a cushion between the vehicle and the road to reduce the transmission of road shocks. The air in the tyre supports the vehicle's mass, and the tread provides frictional contact with the road surface so the vehicle can manoeuvre for normal use. Radial ply tyres are usually manufactured in stages. The casing is initially formed by laying the rubber inner liner and the first layer of textile ply cords around a flat drum mould. The rubber-covered bead wire and sidewalls are then locked into position. The rubber sidewalls protect a finished tyre from curb damage and weathering. At the second stage building machine, the tyre is shaped. Belts of steel wire are guided into place. The tread is then positioned, and the uncured tyre is consolidated by rollers before it is placed in the mould. During the moulding and curing stage, the tyre is subjected to high temperature and pressure, and it takes on its final fixed identity with its own distinctive tread pattern. It is then trimmed and checked for balance and quality before it is inflated and run under load against a rotating drum. This is a final check for ride uniformity. Two types of tyre construction are common: cross-ply and radial ply. The cross-ply tyre is the older form. It is also called a bias ply or conventional tyre. It is constructed of two or more plies or layers of textile casing cords, positioned diagonally from bead to bead. The rubber-encased cords run at an angle of between 30 and 38 degrees to the center line, with each cord wrapped around the beads. A latticed criss-crossed structure is formed, with alternate layers crossing over each other and laid with the cord angles in opposite directions. This provides a strong, stable casing with relatively stiff sidewalls. However, during cornering, stiff sidewalls can distort the tread and partially lift it off the road surface, and that reduces the friction between the road and the tyre. Stiff sidewalls can also make a tyre run at a high temperature. This is because as the tyre rotates, the cords and the plies flex over each other, causing friction and heat. And a tyre that overheats can wear prematurely. Radial ply tyres have much more flexible sidewalls due to their construction. They use two or more layers of casing plies, with the cord loops running radially from bead to bead. The sidewalls are more flexible because the casing cords do not cross over each other. However, a belt of two or more bracing layers must be placed under the tread. The cords of the bracing layers may be of fabric or of steel and are placed at 12 to 15 degrees to the circumference line. This forms triangles where the belt cords cross over the radial cords. The stiff bracing layer links the cord loops together to give fore and aft stability when accelerating or braking, and it prevents any movement of the cords during cornering. The cord plies flex and deform only in the area above the road contact patch. There are no heavy plies to distort, and flexing of the thin casing generates little heat, which is easily dispersed. A radial ply tyre runs cooler than a comparable cross-ply tyre, and this increases tread life. Also, a radial tyre has less rolling resistance as it moves over the road surface. The sidewalls of radial ply tyres bulge where the tyre meets the road, making it difficult to estimate inflation pressure visually. It needs to be checked with an accurate tyre gauge. Using correct inflation pressures extends tyre life and is vital for safety. Sidewalls of an underinflated tyre flex too far, which pushes the centre section of the tread up and away from the road surface. This causes wear at the shoulders of the tyre. In an overinflated tyre, the sidewalls are straightened, which pulls the edges of the tread away from the road and causes wear at the centre of the tread. A tube-type tyre uses an inner tube, which provides an airtight container inside the tyre. A tubeless tyre is lined with a soft rubber layer to form an airtight seal. This inner liner also seals against small penetrations, letting air escape only relatively slowly. When a tubeless tyre is fitted, an airtight valve assembly is used. It can be a tight fit into the rim or be held with a nut and sealing washers. A tyre and wheel assembly must be balanced. As the wheel rotates, centrifugal force acts outwards. Any part heavier than the rest will vibrate vertically, with the heavy area slapping the road surface with each turn of the wheel. This is called static unbalance. Dynamic unbalance causes the wheel assembly to turn inwards and then outwards with each half revolution. As speed rises, rapid side movement of the front wheels causes a sideways vibration or wheel wobble effect at the front of the vehicle. These conditions must be corrected to prevent cupping or dishing of the tread and reduced tread life. Tread life can also be reduced by incorrect wheel alignment. The feathered edge of this tyre indicates an incorrect toe setting. And wear on the one shoulder of this tyre could be due to incorrect camber setting. Most passenger car tyres have tread wear indicators moulded into the tread pattern. They generally provide an indication when the depth of a tyre groove falls to 1.5 millimeters. Control of a vehicle in any weather conditions depends finally on frictional forces generated between the tyres and the road surface. On a dry road, a smooth rubber surface can provide a high coefficient of friction, sufficient to maintain a degree of control during braking, accelerating, and cornering. In wet conditions, the coefficient of friction between a smooth tyre and the road surface falls to an extremely low value. Grooves in the tread pattern clear water away from the contact patch area. This allows a relatively dry area to be formed and for road adhesion to be maintained. During cornering, centrifugal force acts on a vehicle to produce a side force. This side force must be resisted by the interaction of the tyre on the road surface. The greater the side force, the greater the opposing force must be. Without this resistance, the vehicle will continue in a straight line. The pneumatic tyre provides this opposing force by being able to distort while still gripping the road. Then, since the tyre's construction makes it elastic, it exerts a force called cornering force, which acts between the tread and the road surface. It pulls the distorted rubber back to its normal position. The tyre's sideways distortion makes the vehicle follow a path at an angle to the direction the road wheel is pointing. This is called the slip angle. As cornering force increases, so does slip angle. This vehicle is being driven into a turn with decreasing radius. Both slip angle and cornering force increase until a point is reached where the tyre slides, and the only resistance comes from sliding friction across the road surface. The tyre grips again only when the vehicle has slowed or is making a turn with a larger radius. That is, when the side force is reduced to a level the tyre can withstand without skidding. Since both front and rear tyres develop a slip angle in a turn, the vehicle's path is determined by the steering of the front tyres and the slip angles of both the front and rear tyres. These slip angles depend on the location of the major components. The centre of gravity is the balance point of the entire vehicle. Its actual position depends on location of the major components. It is always located above the road surface and between the tyres. When a vehicle is cornering, this is the point through which all centrifugal force is assumed to act. Its position is determined by the load carried by the front and rear wheels, that is, by how weight is distributed. This is a 40%, 60% fore and aft weight distribution. 40% of the weight is carried on the front wheels, 60% on the rear, and the centre of gravity is closer to the rear than the front. A weight distribution of 60-40 has the centre of gravity closer to the front than the rear. Lateral weight distribution can be expressed in the same way. The height of the centre of gravity is determined by the height of the mass above the road surface. Every vehicle has static weight distribution, whether it is at rest or travelling in a straight line at a steady speed. This is changed laterally by centrifugal force when the vehicle is turning, and in a fore and aft direction during acceleration or braking. During cornering, centrifugal force puts more weight on the outside wheels. Acceleration puts more weight on the rear wheels. Deceleration or braking has the opposite effect. In a turn, centrifugal force tries to push the vehicle away from the corner. This is resisted by the cornering force of the tyres. The tyres have slip angles due to the cornering forces acting on them. And since the cornering forces at front and rear may not be equal, the slip angles at front and rear can be different too. With the centre of gravity closer to the rear tyres carry more of the weight, so they operate at a greater slip angle than the front tyres. Larger side forces act on the rear tyres, which causes greater tyre distortion. This condition of higher slip angles at the rear causes oversteer. More weight on the front tyres means they corner with greater slip angles than the rear. The vehicle is then said to understeer. With equal slip angles at front and rear, the vehicle is said to have neutral steer. Radial ply tyres generate much higher cornering forces than cross-ply tyres, which is why the two tyre types should not be used on the one vehicle. Slip is also influenced by inflation pressures, so manufacturer recommendations should always be followed. This section examines tyre materials. Modern tyres are made from a range of materials. The rubber is mostly synthetic, with carbon black added to increase strength and toughness. When used in the tread, this combination gives a long life. Natural rubber is weaker than the synthetic version. It's used mainly in sidewalls. The pliers are made from cords of fabric coated with rubber. Early tyres used cords of cotton, but with increased vehicle speeds and loads, rayon and nylon cords are now common. Cords of synthetic fabric have high tensile strength. They resist stretching, but are flexible under load. The cords are placed in parallel and impregnated with rubber to form sheets called plies. Plies have high strength in one direction and are flexible in other directions. When cotton was used as a cord, the number of plies or layers in a tyre was a measure of the tyre's strength. Newer cord materials use fewer plies. A modern steel-belted radial with a 6-ply rating may have just 2 plies in its sidewall. Having fewer plies makes the tyre more flexible. Higher numbers of plies make a tyre's response to bumps harsher. The bead of the tyre is made of a cord of high-tensile steel coated with rubber. The end of the ply is wrapped around the bead, which is then wrapped in rubber to stop chafing of the plies, and also to seal the bead against the rim. The length of the wire used for the bead determines the rim diameter of the tyre. Belts that reinforce the tread area of the tyre are mostly made of braided high-tensile steel wire, but they can also be made of rayon or polyester. The inner liner of a tubeless tyre is made of soft rubber. The inner liner must be flexible and airtight. This section examines tyre sizes and designations. The size of a tyre must satisfy some basic conditions. The bead diameter must suit the wheel rim diameter. Section width must be suitable for use on the wheel rim and large enough to have a suitable load-carrying capacity for the vehicle. The overall tyre size must allow sufficient clearance between the tyre and the vehicle frame. All manufacturers mould information about the tyre into its sidewall. In cross-ply tyres, the bead diameter and the section width are stated in inches. For example, 600 by 16 indicates a tyre with a section width of 6 inches and a bead diameter suitable for fitting to a rim which is 16 inches in diameter across the bead seats. The load capacity is indicated by the ply rating, for example 6 PR. The aspect ratio of a tyre is the ratio of its height to its width. It is usually given as a percentage. The lower a tyre's aspect ratio, the wider the tyre is in relation to its height. An aspect ratio of 98% means the section height of the tyre is slightly less than the section width. This is called a cushion or balloon tyre. An aspect ratio of 88% means the height is 12% less than the width, giving a lower profile. It is called a medium-low profile tyre. The profile of cross-ply tyres was reduced further to between 78 and 82%, called a super low section. However, the stiffness of cross-ply tyres makes them unsuitable for further reduction in profile. Radial ply tyres have been manufactured in 78% profile, but are also made with further reductions in profile from 75% to 45%. Information on tyre aspect ratio is now included in the sidewall marking, together with the type of construction and the speed rating. The speed rating of the tyre is given by the letter code, which indicates maximum recommended speed for that tyre. Common symbols for passenger car tyres include S for up to 180 km per hour, H up to 210 km per hour, V up to 240 km per hour, and Z for over 240 km per hour. Radial ply tyres have always been marked with the section width in millimetres, but with the rim diameter in inches. For example, on this tyre, 185 is section width in millimetres. 70 indicates a 70% aspect ratio. H is the speed rating for up to 210 kilometers per hour. R indicates radial ply construction. 13 indicates the tyre is suitable for fitting to a 13-inch diameter rim. Totally metric types are also manufactured. Here, 190 is the section width in millimeters. The aspect ratio is 65%. The speed rating is H for up to 210 kilometers per hour. R indicates radial ply construction. 390 indicates the tyre is suitable for fitting to a 390 millimeter diameter rim. Metric diameter rims cannot be fitted with inch diameter tyres, or vice versa. Although tyre markings may remain traditional, say 255/45 ZR17, there is a worldwide move towards an ISO metric standard which uses letters P for passenger, LT for light truck, C for commercial, and T means temporary use as a spare wheel. The tyre may have a load index number indicating the maximum load a tyre can carry at the speed indicated by its speed symbol, which follows the number. So a P-series metric size code may read in full P205/65 R15 92H. P for passenger car tyre. 205 is the section width in millimeters. 65 for 65% aspect ratio. R, radial ply construction. 15-inch diameter rim. 92 load index for a maximum load of 630 kilograms. And H for a speed rating of up to 210 kilometers per hour. Further development of high-speed tyres has expanded the speed categories to include W and Y. For this tyre, Z indicates a speed over 240 kilometers per hour. But the load and speed rating is taken as the maximum load and speed. That is 89 for a maximum load of 580 kilograms, and W for 270 kilometers per hour. This section examines basic principles of wheel alignment. All wheels of a vehicle must be correctly positioned with the vehicle and with each other for the vehicle to drive and steer properly. A driver should not need to keep manipulating the steering wheel to maintain the vehicle in a straight-ahead position on straight, level roads. Similarly, little effort should be needed to turn the vehicle into curves or to let it return to the straight-ahead position when the curve has been negotiated. Wheels are installed on the suspension units at certain angles to provide for these factors. These angles taken together are called wheel alignment. The factors that affect wheel alignment are camber, caster, steering axis inclination, toe in, toe out, and toe out on turns. This section examines caster. This is the steering axis centerline. Seen from the side of the vehicle, it is normally tilted from the vertical. Caster is the angle formed by this line, and a line drawn vertically through the center of the wheel. Backward tilt from the vertical is positive caster. Forward tilt is negative caster. When a vehicle has positive caster, a line drawn through the steering axis centerline meets the road surface ahead of the centerline of the wheel. The tire contact point is behind the steering axis. When the wheel is turned to the right, the tire contact point is moved to the left of the direction of travel. And similarly for turning to the left. In forward motion, this generates a self-centering force which helps return the wheels to the neutral position when the steering wheel is released. The effects of positive caster can be seen in the motion of this furniture wheel. When it is acted on by a forward-moving force, Its pivot point ahead of the wheel ensures the wheel always trails behind. Most cars have positive caster because it makes it easier to travel in a straight line with minimal driver action. But as positive caster increases, more and more effort is needed to turn the steering wheel. A small amount of negative caster reduces the steering effort needed at low speeds, but can make a vehicle wander at high speeds. In all cases, the manufacturer's specifications should be followed. This section examines camber. Camber is viewed from the front of the vehicle, and it is the angle of tilt of the wheel from the vertical. A wheel that leans away from the vertical at the top is said to have positive camber. A wheel that leans towards the vehicle is said to have negative camber. On earlier vehicles with narrow tires with a large diameter, large camber angles were used to bring the center line of tire-road contact closer to the steering axis. It also ensured the vehicle weight was carried by the large inner bearing. On modern vehicles, however, tires are wider, but they are generally smaller in diameter, and large camber angles would produce excessive wear on the outer edges of the tires. The amount of camber is now reduced, so that most cars have what is called zero average camber to give long tire life. This is because when a vehicle is in motion, zero camber is difficult to maintain. Changes in running camber can be caused by road irregularities and load variations. This section examines scrub radius. Scrub radius is also known as steering offset and scrub geometry. It is the distance between two imaginary points on the road surface. The point of center contact between the road surface and the tire, and the point where the steering axis center line contacts the road surface. If these two points intersect at the center of the tire, at the road surface, then the scrub radius is 0. If they intersect below the road surface, scrub radius is positive. If they intersect above the road surface, scrub radius is negative. The effective scrub radius, positive or negative, is to provide a turning moment which attempts to turn the wheel away from the central position when the vehicle is in motion. On a rear-wheel drive vehicle with positive scrub radius, the vehicle's forward motion and the friction between the tire and the road causes a force which tends to move the front wheels back. This would cause the wheels to toe out. If it has negative scrub radius, the front wheels again tend to move back, but this time they toe in. On front-wheel drive vehicles, the opposite occurs. Positive scrub radius causes toe in, and negative causes toe out. During braking on any type of drive, if braking effort is greater on one side of the vehicle than the other, positive scrub radius will cause the vehicle to veer towards the side with the greater effort. Negative scrub radius will cause the vehicle to veer away from the side of greatest effort. How much it veers depends on the size of the scrub radius. This is why vehicles with a diagonal split brake system have negative scrub radius built into the steering geometry. If one half of the brake system fails, then the vehicle will tend to pull up in a straight line. Since the offset of the wheel rim determines where the center line of the tire meets the road surface, it is important that the offset is not changed if wheels are being replaced. Changing the rim offset changes the scrub radius, and also the predictability of the vehicle handling if brakes should fail. This section examines steering axis inclination. The axis around which the wheel assembly swivels as it turns to the right or left is called the steering axis. It is formed by drawing a line through the upper and lower pivot points of the suspension assembly. Seen from the front of the car, it is tilted inward. The angle formed between this line and the vertical provides steering axis inclination angles. Steering axis inclination acts with caster to provide a self-centering of the front wheels. When the wheels are in the straight ahead position, the ends of the stub axles are almost horizontal. When the wheels turn to either side, the effective steering axis inclination is to make the ends of the stub axle tend to move downward, but this is prevented by the wheel. The stub axle carrier then must move up, which raises the front of the vehicle. When the steering wheel is released, the mass of the vehicle forces the stub carrier back down, which pushes the wheels back to a central position. With a vertical steering axis, no self-centering would occur. The wheel would pivot on a radius with the steering axis as its center. This would introduce a turning moment on the wheel. Road shocks would be transmitted back to the steering wheel, and steering would be difficult to control. Steering axis inclination brings the pivot point close to the center of the tire contact patch at the road surface. It intersects with the camber line drawn through the tire and the wheel. If these two lines intersect at the center of the tire at the road surface, then the vehicle is said to have zero offset or zero scrub radius. If they intersect below the road surface, then it has positive offset or scrub radius. If they intersect above the road surface, then it has negative offset or scrub radius. The angle between the steering axis inclination and the camber line is called the included angle. It is a diagnostic angle. Since the steering axis inclination is not adjustable, if the camber angle is correct, then the steering axis inclination should also be correct. That is, it should match the specification. This section examines toe in and toe out. When the front of the wheels, as seen from above, are closer together than the rear of the wheels, it is called toe in. The opposite arrangement is called toe out. The static toe setting is designed to compensate for slight wear in steering connections, which may cause the wheels to splay outwards or inwards. This means the wheels will be parallel when the vehicle is in motion, which avoids tire scrub. This section examines toe out on turns. Toe out on turns is the relative toe setting of the front wheels as they turn to left or right. When a vehicle makes a turn, each wheel should rotate with true rolling motion that is free from tire scrub. True rolling motion is only obtained when each wheel is at 90 degrees to a line drawn between the swivel axis and the center of turn. Because the rear wheels are fixed, the center of turn will lie somewhere along the center line of the rear axle, depending on how far the steering wheel is turned from the straight ahead position. To provide true rolling motion, the inner wheel must be turned through a greater angle than the outer wheel. This allows the inner wheel to turn through a smaller turning radius than the outer wheel. This automatically correct alignment is obtained by use of the Ackermann principle at layout. With the steering linkage at the rear of the wheels, the distance across the tie rod ends of the steering arm joints is made shorter than the distance across the steering axis swivels. This forces the inner wheel to turn through a larger angle when the steering is turned. The Ackermann angle is the angle the steering arms make with the swivels on the center line of the vehicle at or near the center of the rear axle. This section examines turning radius. Turning radius is a measure of how small a circle a vehicle can turn around in when the steering wheel is turned to the limit. All vehicles have stops to limit how far the front wheels can turn. In some designs, these stops can be adjusted as part of a wheel alignment. If the stops are incorrectly adjusted, they could allow too large a turning angle, and the steering box can be damaged.